We did number one, we're doing number two, the second welfare theorem. The first welfare theorem said that every competitive equilibrium is Pareto efficient. And what I mean by that is the outcomes of the competitive equilibrium, the resulting allocations under the prices, constitutes a Pareto efficient allocation. The second welfare theorem runs in the other direction. It says if we start with a Pareto efficient allocation, we can find some transfer of wealth to make that particular Pareto efficient allocation the result of a competitive equilibrium. So we can make it stable under a market structure. Now, we might have to transfer wealth between agents because remember, if we have strictly monotone preferences, we have two agents. If we give everything to agent one, that's Pareto efficient. But if we start with the allocation where agent two owns everything, then of course there's no prices which are going to get agent two to give away everything to agent one and get nothing in return, right? That's it's totally crazy. So it's not saying that every Pareto efficient allocation is reachable by any initial endowments, but that there are some initial endowments which make it the solution or whatever, the outcome of the competitive equilibrium. And so this seems like it's kind of weak, but it's an important theorem in that what it says is that if we reach some Pareto efficient position, then there's a system of prices which would keep us there, which will make it a stable point in equilibrium. It also says that all we really have to do is transfer wealth between people, and they'll eventually get to the Pareto efficient allocation. So in a slightly more general form than I'm presenting it here, you could just transfer money to different agents. So in other words, you could tax them and then reallocate the taxation, and that would bring us to a particular Pareto efficient allocation. But we're not covering that here. So let's state the theorem. It says if Ui omega I is an economy, so utility functions and endowments for each agent, U is continuous and strictly monotone, and then we pick out some Pareto efficient allocation, X asterisks, then there exists an equilibrium where we might have to change the endowments such that the resulting allocation in that equilibrium is X star, X weak star, whatever, the asterisk symbol. So omega really plays very little role. It just says if we have, it tells us what's efficient, right? It tells us what's feasible, but other than that, it's not really playing a role. We're allowed to shift the omega. We're going to prove it on this slide. Very simple proof. It's essentially so simple it seems like we're cheating. What we're going to do is we're going to let the endowments be omega I be X star I, right? So we're just going to trade around the people to be at the feasible position we want. And of course that seems like we're cheating, but the point is that then there exists a price vector which supports this, right? Which means that people don't want to move away when we have these prices. So once we've reached this Pareto efficient point, there's prices that keep us there, is the point of the theorem. So by the existence theorem from a few videos ago, we have that under this new allocation, under this new endowment omega I equaling X star I, there exists some equilibrium. We're just going to call this P and an unadorned X, an X with no hat or star or anything. So Px is an equilibrium. We know that such an equilibrium exists because we have the conditions of continuity and strict monotonicity. And whatever, convexity, just whatever you need. Give me everything you need. Since X star is affordable under P, right? Remember, your endowment is always affordable. So X star is affordable because X star was the endowment. And you sell the stuff to the state, you can buy it back from the state, the prices don't change. So using that same, using the fact that X is the Walrasian demand under this budget and price vector, we know that the Walrasian demand is the maximum utility, which means that Ui of X must be greater than or equal to Ui of X star, right? Because it's a Walrasian demand, it must be better than X star. But X star is Pareto efficient. And if X star made everybody better off, it couldn't make everybody better off and anyone strictly better off, right? Because then that would be the opposite of X star being Pareto efficient. So the fact that X star is Pareto efficient means that the reverse inequality also holds, right? Because think about it in the other way. If there was some point where there was some J such that X star I was strictly bigger than X star x ui of xj, uj of xj was strictly bigger than uj of x star j, then that would mean that x star wasn't Pareto efficient. So in other words, ui of xi equals ui of xi star for every I. But what does that mean? That means that these provide the same utility to every agent. So they're affordable and they provide the same utility, they're while raising demands. And hence, P, that original price vector, and X star is in equilibrium. And it could turn out that X star is the same as X, right? These might be the same point, but even if they're not the same point, they provide the same utility, so they're both equilibrium. So the point that is the point. The intuition behind this proof is that if we begin with a Pareto optimal allocation, trading can't make anyone better off without hurting someone. And because we don't have to trade, right, agents in a market can keep their endowments. So there's no way to change any consumer's utility, because if they could get better, then it would be hurting someone else. But that other person wouldn't engage with them because they don't have to, right? So let me say that logic one more time. I'm going to say exactly the same thing I did again, but in different words. Each agent is entering the market freely. So they don't have to trade their endowment, right? They could just buy back their original endowment or whatever. They could keep what they started with. What they started with was Pareto efficient, which means in order to make anyone strictly better off, someone has to get worse, has to be made worse off. Well, let's think about that guy who gets made worse off. He could stick with his original bundle, or he could move to this position where he gets worse off. Of course, he's not going to move to the position where he gets worse off. He's optimizing. So it can't be that there's any system under the system of prices. It would push you away from this, right? We can't make anyone better off. So it must have been that this original point was actually in equilibrium, right? Because no one would have traded. No one wants to trade, and so we can't move away from that using prices. There's one more last thing I'm going to talk about really quickly. It's externalities. I'll talk about it in class, but I don't think it's worth making a full video. But externalities is when one agent directly makes the another agent worse off. So the classic example is like pollution. And I just want to make the point that under externalities, the welfare theorems don't hold. And we'll explain why and go into detail in class. But I just don't think, I only have a couple slides on it, and I want to do the stuff in class anyway. So that's it. That's it forever.